Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Good morning. This today we will cover lecture 16 on the relative motion analysis using rotating axis. This will be the last theoretical section before we go for more examples and then we go for tests and so on. So this part is the most one of the most difficult or the more difficult part. So I hope you can pay more attention to this and take your time to analyze this thing. So what do we mean by we have done relative motion analysis previously using translating axis. Now we talk about rotating axis. Okay, so previously we developed the equation using translating axis. In this lecture we will analyze the motion using rotating axis. For example, typical example is how or when we measuring the movement of an object from a rotating platform. In this example, you can take that if you are moving or measuring an aircraft velocity from a vehicle which is not only moving but also rotating. For example, taking a corner. This is one example. Another example is you can look at the Earth and you are measuring the motion of something else relative to the Earth. At the same time, your satellite station, satellite tracking station, your radar station on Earth is on the surface of the Earth, and the Earth is rotating 24 hours per rotation. And how do you adjust for that velocity? So these are the equations or the approach that is being developed, or we will develop this for us to look and how to measure the motion using rotating axis. There are two coordinates axis involved. The first is the fixed axis, which is the XY axis, and second is the rotating axis. The capital XY is the global axis, the small xy is the rotating axis, and the measurement of the object is done relative to the rotating axis. So this is an example of what we have been talking about. So let's say that our global axis is this X and Y. So this is the global axis, and we have a rotating axis, a small X and Y. Yeah, X, this axis is rotating, and we are measuring the movement of a particle B relative to our rotating axis. So this rotating axis has its origin at A, and it is now rotating at a speed of angular speed or angular velocity of omega, and also angular acceleration of omega dot. So let's say for this instant, the position of B is determined by this coordinate xb and yb. So we can say that xbi, ybj is the coordinate of the system. So we can write the coordinate system. For example, we can write here that B is xbi and ybj. So that is the coordinate of system. And these are measured relative to the rotating axis xy. So sometimes we put that subscript xy as to make sure that we are measuring relative to B. And therefore, and from there, we have the position vector of the origin of the rotating coordinate system, rotating axis as A, and we put that as position vector A. And B relative to A is the position vector of B relative to A, B measured from A. If you are at A, you are measuring this position vector, and we know that it's the position vector, the coordinate is given by xbi, ybj. And finally, of the position vector rather than coordinate, the position vector is given. So let me correct that. So the vector is xb and yb. That is the coordinate of B. The position vector is xbi, ybj. So and then we have this final position vector B. This position vector B is the position of B measured relative to the global axis. So let me ask you a question. Is this global axis moving? The answer is no. The global axis is fixed. So global axis is fixed. Let's write down. Global axis is fixed. Axis fixed. What is moving? The moving are, this is global axis. The movement are for the rotating axis. This can move at a certain velocity. For example, the origin of the rotating axis xy can move. It's moving at a velocity va and acceleration aa. So it has a velocity and acceleration. So it has velocity a and it's also accelerating at a. Okay, so we've got this data. What is the speed of a and what is the acceleration of a and the angular velocity of the rotating axis and the angular acceleration of the rotating axis. So we have drawn the position vector RA, RB relative to A, and position vector B. So we can write the equation of the position vector as position vector B equals to position vector A plus position vector B relative to A. This is our equation 1. We have done this many times before. So in the relative motion analysis, we have done this and we have used the same nomenclature. So I think this is quite clear where the position vector equation comes from. Position vector B equals position vector A plus position vector B relative to A. So this is our equation 1. So from that position vector equation, so position vector B equals to position vector A plus position vector B relative to A. We differentiate it in order for us to get the velocity B. So we differentiate RB, we differentiate RA, and we differentiate position vector B relative to A. When we because RB is fixed and RA is fixed, so position vector B is not fixed, it means it's not rotating. So position vector B is RB dot. Position vector A will give R dot A, so it's VA. And then we have d over dt, position vector B relative to A. But B relative to A is given by this vector. Okay, but position vector B relative to A is given by xbi plus ybj. And remember, I and j is a rotating vector. Why we can't do it directly? Because I and j is a rotating vector and it has a special characteristics or special features. So if we differentiate d over dt position vector B relative to A, we can now differentiate the whole term here, xbi plus ybj. So d over dt xbi plus ybj, and we can then differentiate in term d over dt xb times I plus xb di over dt, and so on, d over dt yb times j plus yb times dj over dt. Now, d over dt of xbi here is quite straightforward. Will give us x dot bi, and d over dt yb we will get y dot b because it is not a rotating vector. However, and we can combine that to become x dot bi plus y dot bj, and we have that is equivalent to the relative velocity of b, the velocity of b relative to A, or we put it here as it's the same thing here, yeah. So this is an equation that we want to keep. X dot bi plus y dot bj equals to vb relative to A. The same thing is written here, though it's hidden to you because of the picture. So yeah, so you can see that this is x dot bi plus y dot bj. You have this is the relative velocity measured from xy. So this is for better or clearer with notation xy. We started to put the notation here because all these measurements are done in the rotating axis system xy. So what's next? We have got two more terms that we have not evaluate xb di over dt and yb dj over dt. So we need to now go and look at this term. So just now we have d over dt, position vector b relative to a. We have I dxb dt and y dyb dt, and that gives us this one as before. Let me put it down here. It gives us x dot bi plus y dot b j, yeah, and that is can be written as this one is in terms of small xy. Okay, so that we can write it down as relative velocity of b relative to a of xy. We have got two more terms which we have not evaluated, which is the first term is here. First term is here, di over dt, sorry, and the second term is dj over dt. So now this is a big jump from di over dt equals to di over dt is equals to omega cross I, and dj over dt is equals to omega cross j. To prove this, you have to go and read the textbook, because if I were to explain here, it would take a bit more time. You have to read it several times to understand where it comes from, but it's okay for you to accept for now that di over dt for a rotating axis, for a rotating unit vector, is equivalent to h omega, the angular velocity, cross the unit vector itself, and dj over dt equals to omega cross j. So then we now substitute di over dt with omega cross I, so we get xb omega cross I, and yb dg over dt we substitute with omega cross j. We had yb omega cross j, and therefore we can write it down as omega cross xbi. Yeah, so sorry, there's a mistake here. That is what's supposed to be is I. Use the right color. I is the one that is the vector, not xb. So this one, there's no xb here. Yeah, so it's omega cross xbi plus omega cross ybj. I just put the yb in front of the terms j here, and xb transferred to here. Okay, so then we can have this equation that when you differentiate d over dt rb relative to a, we will have vb relative to a xy. Yeah, this is measured xy plus omega cross xbi plus ybj, and we know that xbi plus ybj is position vector b relative to a. Yeah, we've done this before, and so this one is here, and then this is equals to vb of relative to a measured from the xy axis plus omega cross b relative to, actually everything is measured relative to the rotating axis. So so we have this equation 2a on the top, and equation 2b is vb equals to va plus vb relative to a xy measured from xy, and gamma cross position vector b relative to a. This is equation 2b. So the velocity of b equals to the velocity of a plus the velocity of b relative to a measured in the xy axis plus omega cross position vector b relative to A. So this is the equation for the velocity. So we label it as 2b. Okay, so let's move on to the next one, which is the acceleration. So for acceleration, we got from before the velocity equation, which is equation 2b. So we got VB equals to VA plus VB relative to A xy. Sometimes we call it V relative plus omega cross position vector B relative to A. So this is the equation 2b. So I might want to block it and see that, because it would be better for us to come back to here. So this is equation 2b. So we will now differentiate velocity b, dvb over dt, and we have to differentiate all these three terms: va, vb relative to a, or v relative, and the term omega cross position vector b relative to a. So this is what we have written down here: dva over dt, d over dt, vb relative to a. xy is the reference. This is a subscript, not a value. And d over dt is omega cross position vector b relative to a. Okay, so we have this big equation that acceleration b, vb over dt, dvb over dt is ab, because vb is not rotating. Va, dva over dt is aa, because a is not, the point A is not rotating. And then we've got d over dt, VBA, xy. We now separate it into its component: VBAI plus VBAJ. Okay, it has its two components, I and j. Okay, and plus d over dt omega cross position vector A. So we've got, first we do the differentiation of the omega, d over dt omega cross position vector B relative to A, and then we take the omega out and do the differentiation of d over dt position vector B relative to A. So the first term, d over dt VB relative to A, we have to find the I and j component. So we got d over dt VB over x I plus v over bax di over dt. All right, with that in turn pula, one by one. First we do the differentiation of b relative to a, and then di over dt, and then v over ay, and then we do the dj over dt. So there will be four terms here: 1, 2, 3, 4. So there are two terms each: vbax and then vbay. So vba x is, when we differentiate it, we will have the acceleration in the x component for b relative to a, and we give, and direction is I. And then when we do d over dt vbay, we get aba, the acceleration of b relative to a, in the y component in the j direction. And now we have got vba in the component of x times omega cross I, because di over dt, remember, di over dt, di over dt, di over dt is omega cross I. Similarly, dj over dt is omega cross j. So we have this, and we now put that there, and I am combining the component, the acceleration component. So let's use some color here. Let's use some color. So the light green one is for the acceleration component. So this is the acceleration component, ABAX and AB, acceleration of B relative to A in the Y component. So I put it here, X and Y, and chance of tak boleh. So we are now here. So this is the acceleration component X and Y combined, plus plus, then we have got omega cross V BA xi and VBA yj. So we have now got this as the vector B relative to A. So omega, so that's the, let's do that in yellow. Maybe it's easier to do that yellow. Yeah, the yellow terms goes into the yellow terms. So I've got these yellow terms, VA yj, I and j terms. Yeah, so this one go here, this one goes here, this one goes there, and this one goes here. Okay, so then we get term number 1, d over dt VBA. When we differentiate the relative velocity, we will have the relative acceleration plus omega cross the relative velocity. Omega cross VB relative. It's a long thing. Vector B relative to A measured from the xy coordinate, rotating coordinate. So I said V relative. So omega cross V relative. So this is term 1. So there are 2 more terms that we need to cover. So term number 2 is d over dt omega cross position vector B relative to A. So that we get omega becomes omega dot cross position vector B relative to A. So I didn't put the underline. Omega dot cross position vector B relative to A. So term 2 is quite straightforward. Term number 3. Term number 3 is omega cross d over t position B relative to A. So we have done that this differentiation of position vector B relative to A earlier from equation 2A. If you refer to the earlier slides, position vector B relative to A is when we differentiate it, we will get the relative velocity xy plus omega cross position vector B relative. So we got V relative plus omega cross position vector B relative to A. So when we do the cross operation through these two terms, we will get omega cross the relative velocity xy plus omega cross r. This is similar to our normal assertion, omega cross r, and we can simplify that to minus omega square position vector B relative to A, and then we have got this omega cross the relative velocity. So that is term number 2 done. Term number 3 is also done. So when we have done all the terms, we are now ready to combine them. So when we combine all the terms from equation 3a, we will see that acceleration of B equals to acceleration of A plus acceleration of B relative to A measured from xy. Sometimes I call this A relative, so let me write it down here. I'm using the red color, so sometimes I put as A relative underline. So it's a vector, and plus omega, this first term, the first term omega cross VBA xy. This is also called, I call it V relative. Okay, omega cross V relative plus omega dot cross position vector B relative to A. Sometimes we don't use alpha, so omega dot is okay. And then the third term is omega cross VB relative to A measured in xy, so also called omega cross V relative minus omega square position vector B relative to A. So these two things, I have colored them, highlighted them in green, so you can combine them together. Here we have combined them together to form 2 omega cross V relative. And this omega dot is here, and then this term is coming here. So AA relative to omega cross V relative. So I'm going to put that as also, maybe I should write it down as V relative. So V relative. Okay. So this is acceleration of B and measured from global XY reference. This is the absolute velocity of B equals to the absolute velocity of A plus the relative acceleration, i.e. acceleration of B measured from A using the rotating coordinate XY. It's a long-winded term to say in for this symbol, so we just use A relative. Acceleration of B measured by observer at A using rotating let me put that using, oh my god, it's a long thing, using rotating axis XY. Panjang tu. And omega and omega dot are each angular velocity and acceleration of the XY coordinate system. And then VB relative to XY is the V relative, velocity of B measured from observer at A. And then we got omega dot cross position vector B relative to A minus omega square position vector B relative to A. It is this long equation. Sometimes students ask me whether I should memorize this equation. Sometimes I said there are cases in the examination I ask the students to derive this equation. However, in this online examination, we will not ask you to derive the equation because it's already being derived for you. So here is a long-winded equation, and it's quite heavy for the brain to accept it in the first time. Go slowly, and then from there we will cover what would be the relative, what would be the how are we going to apply in this lecture. So I have made a point not to limit my lecture to about 25 to 30 minutes each, so that it will not be so taxing to the student. But I will stop here. Before that, I just want to share with you. So we will use our system here as before. So that is the previous. So we want to use our known system. So we will write not in the same thing. We will write as V of P, equals to VB here plus omega cross position vector P relative to B plus V P relative to B and the rotating XY. So that's how we map P to this equation, right? So what is the position vector P relative to B? It is 1.5 meter along X. P is 1.5 meter long. So P relative to B is 1.5 I. Right. So we have that. Let us tick that. So we have that. Okay. So what about this one? We have got that. We have done this. What about omega? Do we have omega? Yes, we have omega. We have our omega here. Omega is 0.4 radians counterclockwise. So if it is xyj is in a positive too. So omega. So is it omega? Oh no, lex. Omega equals to omega here equals to 0.4k. Yeah. So this is a few skills that you need to do. What else? It's given also alpha dot, given the angular acceleration here. Yeah. So we know that omega dot equals to alpha equals to 0.8 k unit per radian second square. I'll just put the units here. What else do we need? We need we need omega. We need we do have VA. VA is the speed of the origin. So we have VB. VB is given. So what is VB? VB is known. VB is here, 0.4 meter per second. So VB is 0.4 in the direction of this one. We will have to find the I and J component. So it is 0.5, 0.4 cos 60 degree I plus 0.4 sine 60 degree J. Can you find the resolution here? So if you, this is just in I and J are, I and J is relative to X and Y. So I just said it's moving vertically 0.4. So the angle is 60. So you can find the resolution there. What about acceleration of B? We don't need the acceleration of B. We just, but just in case, so we know that acceleration of B is the same, but it's pointing downwards now. So it's a negative J, and also to the left, and to the bottom. So it's negative 0.2 cos 60 degree I minus 0.2 sine 60 degree J. Unit is meter per second square. This is meter per second. Okay. What else do we need? What is B relative to A? What is P? What is P relative to B? What is this? So we know that P is moving outwards. This velocity of P is actually velocity of P relative to B. So here is, I'm going to write it down, is velocity of P relative to B measured in the rotating XY axis is 0.4 actually. It is at 2 meter per second. 2 meter per second. So V P relative to B in the XY system is 2 meter per second. 2 I in the direction of I. Meter per second. Okay. Do we have anything? Yeah, we have some more points, which is it's also decreasing at the rate of 5 meter per second square. So it's extension, but it's slowing down. So the relative acceleration A P relative to B in the XY system is negative 5 in the direction of I meter per second square. So we have covered all the data, yeah. 0.4, and then acceleration 0.2 for the origin, for the P, and then we've got omega and alpha covered, and relative velocity. So we have covered on how to use this data. So if you use that data now, yeah. So can I remove this? No, I cannot remove that. So therefore, we just put VP. So I'm going to take this equation here. I'm going to take this equation and I'm going to write it here. So I'm going to take that equation and I'm going to write it over here. So VP, VP equals to VA. Do I know what VA is? Yes. VA is VB, sorry. VP equals to VB. VB, I know what VB is. 0.4 cos 60 degree I plus 0.4 sine 60 degrees J plus omega, and I got plus omega. What is my omega? Omega is 0.4k, 0.4k cross. Do I know my position vector p relative to b? Yes, it's 1.5i, so it's, I did 1.5i. Okay, so that's the second term, omega cross position vector p. So I'm going to block that as a separate term. And then finally, what is the relative velocity? Is vb, vp relative to b. I've got here 2i. So my vp relative to b is 2i. So it's plus 2i. So that is the answer to the whole question. That is what is the, that it will be the first answer of VP. Determine the acceleration of point P. We haven't, so let's say we limit this to the velocity of point P. Okay, I am going to stop there just to make you feel comfortable with the examples, and you can follow with the acceleration later on. So I have carried out the calculation here. So we get Vp equals to 0.5 times cos 60i, 0.2i, 0.5 times sin 60j is 0.3464j, 0.4k cross I is j, 0.4 times 1.5 is 0.6 plus 2i, and the answer is Vp equals 2.2i plus 0.9464j meter per second. So that's the velocity of point P. Let's continue with the acceleration. So here I have put up the long equation for the acceleration. Yeah, so it's AP equals to AB plus A relative acceleration plus omega dot cross position P, P relative to B, 2 omega cross V relative minus omega square position of P relative to B. So AB is minus 0.2 cos 60. Where do I get this? Is this from the resolution or the components of vertical deceleration of B, and find the component of I and J is minus 0.1i is minus 0.1732. And then we get the relative acceleration is minus 5i. P is slowing down at minus 5 meter per second square. So, and then we have got omega dot cross. Omega dot is 0.8k cross 1.5. Position vector is 1.5i. Got 1.2j. 2 omega cross V relative. 2 omega. Omega is 0.4k. V relative is 1.5i. Sorry, this is not 1.5i. The speed is extended 2 meters per second. Oh, I made a mistake here. So I've got to correct this. Yeah, this is, the speed is 2i. So 0.4 times 2.8, 0.2 is 1.6j. So it's 1.6j. Okay, and omega square position vector P relative to xy is 1.5i, so 0.25i. So, and finally we've got the acceleration here, AP minus 5.34, 2.26 is not 2.268j, but rather it is we have to add 2.68j. I hope the math is correct. At least the maths are correct. I did make some mistakes here and there, but I do wish that you can follow through. It has been quite a tough example, but it shows you how to apply the all the terms that you've covered in the acceleration into the equation. So the key here is to understand again where is your fixed coordinates here, and where is your rotating coordinate here, rotating coordinate small x and small y, and how it rotates, and from there you apply all this knowledge. We will do several examples to make it more clear to you. Okay, so I hope you can follow the lecture and have some understanding of the fundamentals of relative motion analysis using rotating axis. We'll see you in the next lecture. Thank you.